Thank you very much, Fritz, for the invitation. It's really a great pleasure to be here and a great honor. Can you hear me well? Yes? Okay, great. So the title of my talk is Bender's Adaptive Cuts. That's probably a new term that you didn't hear before. And I will explain you how we apply this new idea, this new technique, to two-stage stochastic optimization problems with linear recourse. But I want to emphasize that this idea can be also applied to deterministic problems. So not only for stochastic optimization, so keep this in mind while I'm explaining the whole idea. And before I start, I want to give credits to my dear co-authors. This is a joint work with Eduardo Moreno, who is professor in Chile at University Adolfo Ibáñez in Santiago, and his former PhD student, Cristian Ramirez Pico, who also came to ESSEC just before the pandemic started. So unfortunately, we had to continue working on this online. He had to leave on March 15, 2020 and go back home. Okay, so before we start, just a brief introduction about the type of two-stage stochastic problems that we are going to study. So we start typically in the deterministic optimization. We have, let's say, some kind of combinatorial optimization problems to solve where we are searching over combinatorial structures, let's say vector X, which is described by a polyhedron. In stochastic optimization, we assume that we deal with uncertainty, that we have to make decisions here and now. Then there will be some uncertainty that will be revealed in the future, and after that we might correct our decisions, or we have to do some additional, let's say, actions that we will call recourse. And these decisions will be parametric. They will depend on what did we do today and what kind of uncertainty has been revealed later on. Right? So this is what we call recourse. And the goal when we are optimizing here and now is somehow to anticipate what will happen in the future and to minimize, let's say, the costs of what we are doing today plus the expected costs of the recourse action. And this is expressed by this optimization term here now. So we have our here and now decisions and the expectation of the recourse that will, of course, depend on the realization of the uncertainty. If we would have a given vector, let's say, call it psi, which is a realization of this uncertainty, we assume that the recourse problem can be described as a linear program. Okay? In this linear program, we have specific assumptions. We will say that the objective function will be deterministic, but that the constraints are subject to uncertainty. Okay? So in these constraints, for our purpose, we will assume that we have what we call a fixed recourse, which means that the matrix associated with the recourse decisions, that we sometimes also call second stage decisions, this matrix is fixed, but the matrix that describes transition from the first stage and the right-hand side, they are subject to uncertainty. So this is what we call transportation matrix sometimes. Okay, so we have first stage decisions, here and now X, second stage decisions Y, which are a posteriori recourse actions. So how do we solve these problems in practice? So what can happen is that this uncertainty can have a support which is of discrete or continuous nature. In both cases, a state-of-the-art methodology is based on what we call sample average approximation approach. So what does it mean? That means that we will sample a certain number of possible realizations of uncertainty, and in this particular case, that means we will sample possible realizations of this matrix and the right-hand side, and then we will look at the expectation value over this sample. So that means that we are approximating the starting problem by looking into a subset of possible scenario realizations, but in the seminal work by Clivec, Shapiro, and Tito de Mello, they have shown that if we can get arbitrarily close to the true optimum, if we sample sufficiently large number of scenarios. Okay? So that means that if we really want to be very precise and to get the true optimal solution, this number of scenarios can be extremely large. And that is now where the Bender's decomposition can help us to take the advantage of when solving these type of problems. So what are we going to do? So now we are moving into this discrete optimization problem, which we call now deterministic equivalent, because stochasticity is now replaced by the deterministic problem, where we have a fixed, possibly very, very large number of scenarios to solve, and this is our approximation of the expected value of the recourse. So to solve this problem, if you think that the variables x are, let's say, binary or integer variables, and the recourse is a linear program, we are actually dealing with a huge mixed integer linear program, as we would have it in a classical Bender's optimization setting. And the first stage variables are those complicating variables, and the second stage variables will be continuous. Now, to translate this into MILP, we have to introduce for each scenario realization an auxiliary second stage variable, which means that the number of variables explodes, because now we will have one variable, call it ys, to represent our recourse decision in case scenario S is revealed. Okay? And so the whole problem, this is our MILP, that I will refer to as deterministic equivalent, becomes something like this. So we have the discrete variables x and continuous variables ys, representing the second stage decision. That is our expected recourse value. And now we have for every scenario one bunch of linear constraints to model. Okay. And now for this deterministic equivalent, and this is nothing new, this is really the theory of Bender's decomposition for stochastic optimization, or what is also known as the L-shaped method. Now we are going to decompose this problem nicely using Bender's cuts. So how do we do that? So if you look at this deterministic problem, and then if you look at the constraint matrix, then you realize that we have this nice block angular structure that we are going to exploit. So if we would fix the value x, which is the value of the first stage decision, then suddenly the whole problem will decompose into as many subproblems as the number of scenarios that we have. So because when I fix the value of x, then each of these blocks can be solved independently. So we have this separability property, the decomposition property, and we will do that, and then we will solve these subproblems independently. And then now we are going to exploit the LP duality. So what do we have here? So the one subproblem looks like this. So we have the minimization of the linear objective subject to linear constraints, where the right-hand side now depends on the choice of x that we are choosing. Well, instead of looking into this primal linear program, we look into its dual. Why? Because when you look into the dual polyhedron that describes all of these subproblems, we realize that because our objective function is deterministic, then this dual polyhedron is the same for all of these subproblems. So it doesn't really depend neither on the scenario nor on the choice of the first stage solution. And so the points, any point of this dual polyhedron can be explained through its extreme rays and extreme points. And then the extreme points of this dual polyhedron will derive what we call optimality Bender's cuts, and the extreme rays will help us to derive what we call Bender's feasibility cuts. Okay? So let's move then to the final formulation. If we do that, we introduce auxiliary variables theta s in the objective function that are going to replace the value of the linear program for the scenario S. Okay? And then these values will be bounded by representing Bender's cuts as extreme points, and these are, let's say, XP stands for all extreme points of the dual polyhedron, lambda, and XR stands for all extreme rays of the dual polyhedron lambda. So with the extreme rays, we are forbidding that the subproblem S is unbounded, so we are getting rid of infeasible points X. And with these constraints here, optimality Bender's cuts, we are making sure that the value theta S will be exactly the value, the optimal solution value for the subproblem S. Okay. And now we are actually getting into what do I want to talk about today. So there are two ways how we could exploit these Bender's cuts when we have to deal with many scenarios. And two standard approaches are what we call multicut Bender's reformulation and single cut Bender's reformulation. So what is the difference? As you can notice, when you compare these two these are now MIPs because the variables x are still integer. So the major difference is in the objective function. So here the variable theta is simply the aggregation. So the variable theta in the single cut reformulation just replaces the full value of the recurse function, whereas in the multicut Bender's reformulation we decompose the problem and we keep one auxiliary variable for each scenario. Right? This allows us to express the cuts which are disaggregated in the case of theta s variables or aggregated in the case of the single cut. Now, what is important is that if you look into the quality of the LP relaxation of these two models, and if you compare them with the LP relaxation of the original deterministic equivalent, they will be all the same. Okay? So in terms of the quality of the LP bounds, there is no difference. However, the major difference comes from the computational perspective, and the major question for you would be, if you are about to implement Bender's decomposition, which option would you choose? Will you go for multicut or single cut? And there is no unique answer to this question, because it depends on the applications, because each of these approaches has some pros and cons. And so now let's talk about what would be let's say, the advantage of multi-Bender's cuts. The advantage is that because you're disaggregating these constraints, you will add much less iterations, because we are separating these constraints dynamically, until you reach the optimal LP relaxation value. In contrast, with the single Bender's cut, you will have to have many more iterations. What is the disadvantage of the multi-cut approach? The problem is that you might, if you have a huge number of scenarios, that you will quickly overload the master problem. That you might end up adding tens of thousands of cuts. And in each iteration, what we are doing is we are solving the relaxed master problem, which means we are looking at a subset of these scenarios. For the optimal solution, we generate a new cut and we iterate, right? And so we have either the bottleneck in solving the huge master problems, or the bottleneck that the convergence is very slow. And that was the major motivation for us. So the question was, can we find a combination of the two to take advantage of the best of the two worlds in such a way that we can draw computational advantage? And yes, the answer is yes. And this is what is the combination of these best two worlds is what we call adaptive Bender's cuts. And so what is the major idea behind? The idea comes from the previous work of Eduardo and Christian. They have published that recently in Mathematical Programming 2022. And this approach is called Generalized Adaptive Partitioning Method. And this is the idea of solving two-stage stochastic problems in which we do not solve the huge problem with the deterministic equivalent with a huge number of scenarios, but we rather start with a small partitioning of these sets of scenarios and then dynamically, let's say, decompose these scenarios until we reach the convergence. Okay? So, let's see. So this is what I said, generalized adaptive partitioning method. And this was developed for problems without looking into Bender's decomposition. So what is the idea? Let us assume, for example, that we don't work with tens of thousands of scenarios, but with a very few numbers of them. So you partition this set maybe just in 3 or 4 scenarios. And so let's P be that partition of this set. Now, for each of these partitions, we are going to take one representative scenario, and we will then solve the problem just with these representatives. How do we choose a representative? You take an average scenario. So for the so P1 means that's a bunch of scenarios. P2 is another, so it's classical partition. And then TP is the transportation matrix obtained just by averaging all the coefficients of the scenarios which are inside of that partition. And you do the same for the right-hand side. Okay, so that means we are really treating now the whole problem as if we have T many scenarios instead. And then we solve this problem as an MILP, okay, as a two-stage stochastic problem, deterministic equivalent, with respect to this. And now the question is, what do we get? Is this something useful? do we actually get the optimal solution? Can we stop? Or do we have to now somehow refine this partitioning and continue? And so they have provided optimality conditions under which we will know, once we have this partition and the optimal solutions and the optimal dual solutions, we will know whether the solution that we get is optimal for the starting problem or not. And if it is not, then we will have somehow to refine the partitioning. We will do it in a nested way. All right? So I will split P1 into some smaller subsets, P2 into some smaller subsets, and so on, and I will repeat this procedure. So the hope is that we will not end up with the whole set of scenarios, because in the end of the day that will be, but then that's an overkill. But we will stop after very few refinement iterations, and we will end up with optimal solution while solving much smaller deterministic equivalents. And so that was really a nice idea, but as I said, the key point for them was that they were solving here the deterministic equivalent. So we were wondering, can we actually apply now this idea to Bender's decomposition? So the idea was, instead of solving here huge MILPs, let's derive Bender's cuts for these type of partitions, and let's refine them, and let's do this dynamically. So, and if we have here MILPs, what we would do is we will have a single tree implementation, which means branch and cut, which with the cuts which are globally valid, that can be applied so that we have a single branch and cut tree in which we can incorporate this dynamic partitioning idea. Any questions so far? Okay. So that's it. And so if we now replace this step here, so we take this partition P and we solve it, instead of solving deterministic equivalent, we model it as using Bender's cuts. This is what we get. So for the partition P, we get the value where we can solve a MIP in which we now treat the partitions as single scenarios, and we take the average of these, which means the transportation matrix on the right-hand side, they look like that. Okay? And if we solve these problems, what we get is a lower bound to the origin, to the optimal solution of the problem. Why? Because it's just a relaxation. We are not considering all scenarios, but just a subset of scenarios. And so if we have a mechanism to dynamically refine these partitions, so maybe we start with just one single scenario, which is average across all of them, and then we refine, we will, of course, improve the bounds. And in the worst case, if we have to refine it until the whole set of scenarios, we have the same solution. Okay, good. So next, I want to show you now the conditions under which, and this is really not nice to read, but these are the optimality conditions that you have to check in order to be sure that the optimal solution that you get by solving approximated problem with a given partition, is also optimal for your starting problem. Okay, so what are these conditions are saying is the following. You have separate conditions for the right-hand side and for the transportation matrix. And we are multiplying here dual multipliers, optimal dual multipliers lambda, that we get for a given solution of the problem. Okay, so if X is our current solution, for which we solve the recourse problems for each of the scenarios, we get lambdas as optimal dual multipliers, then what is this saying is, if you first multiply lambda with the right-hand side and then take the average, or you take average and then multiply, if these terms are equal, then we can stop partitioning and the solution of the partition problem will be optimal for the starting one. This you can check easily because you just have to plug in the values that you get at the current iteration. But the question is, if this property doesn't hold, what should be the criterion based on which we want to refine partitions, right? Because I was starting with a given partition, and it's not true everywhere. So how can I split them now? Okay? And in the starting paper by Song and Lütke, they have proposed that we just focus on the dual variables. And so we say, okay, here I have a partition P, an element of the partition, which is set P. And if all dual variables for all the scenarios S inside of P are the same, I still keep them together because I gain nothing by looking into them separately. But those that are different, I have to split. And then there are other more advanced criteria, actually, because if you look into these conditions, maybe they can be satisfied even without imposing such a strong constraint, because we can exploit sometimes the structure of this transportation matrix or the right-hand side. And I will just show you two examples, two case studies where we did that. So we were not just focusing on the dual variables, but also, but a little, we exploited it a little bit in a better way. So that's the key result. So we have the conditions under which we know we can stop the stopping conditions for not refining any longer. And also here you can really come up with different types of heuristics how to refine this partitioning if this doesn't hold. Okay. And so these are the two case studies that I want to talk about. One is the stochastic multi-commodity flow formulation, and the other one will be facility location problem with conditional value at risk. Because we will see that Benders is really powerful not only for classical expected value optimization of two-stage stochastic problems, but also it can be nicely applied to CVaR as well. Okay, so what is now the problem that we are looking at? So let us assume that we are given a network, and this is one of the classical problems in transportation or telecommunication, and we have many commodities. So the commodities are goods that have to be transported from the origin to the destination. And now we will assume that the demand of these commodities is not known. It's uncertain. So we transport, for example, the green commodity from the source to the destination. They can be split. The demand can be split across different paths. And what we have to respect are the links in this network, because the links will have certain capacity. Okay? So we have to route, when we route a single unit of the demand of commodity K along an arc, we have to pay these costs,Cijk. And what we have to decide in the first stage is how do we design the network, which means which of these links will be activated and with which capacity. So that is our capacity Uij that we want to install on each of these links, so that the routing costs in expectation across all different scenarios will be minimized in such a network. Because once the uncertainties are revealed, we are going to find for each of these demands appropriate least cost routing solution. So let's look at the MILP. It's not difficult. So we will assume for now, for this case, that the variables X are also continuous. So we have an LP, pure LP, to solve. We have fixed costs for Xij, for installing Xij units of capacity, and then we have the recourse, which corresponds to the routing costs. So for each scenario S, and then again the problem decomposes by the scenario, we have now the realization of the uncertain demand for commodity K in scenario S, and we have the capacities that have been installed in the first stage. So X bar is our first stage decision. And we are solving here the mean cost flow problem, right, with given capacities. Okay, so what can we do now? Well, of course, we can apply the standard Benders decomposition. We will assign dual variables, we will derive cuts, we can apply single or multi-cut approach. But we can also apply our adaptive Benders. And what happens if we apply the adaptive Benders? Well, there are now some observations, because now we have to go back to optimality conditions. So the matrices, the transportation matrix is here all the same for all scenarios. So this is, again, a special case. And these right-hand sides are all the same also, except for the origin and the destination. So here, so this is our right-hand, because that's our transportation matrix, and this is the right-hand side. And here the transportation matrix, and the right-hand side that depends on x, right? And so this is the age vector. These are all the same. And so because of that, when we plug in, when we exploit this information for our optimality conditions, we see that using these as criteria for the refinement, we get something much stronger than just refining based on the value of the dual variables. Okay, so that's the major idea behind. So let's see how it works in practice. So we considered more than 500 different instances from the Rahmaniani, which was also cited by John today, who worked on this problem. And the instances are quite small. If you think these are really small networks, you have 10 nodes, 60 arcs, and between 10 and 50 commodities. But then you have to multiply all of that with the number of scenarios. You multiply these numbers with the number of scenarios to get actually MILPs with millions of variables in this case, right? And so let's see what happens if we consider these free implementations. And I have to say that these are really vanilla implementations because we didn't want to combine this with more advanced stabilization effects or any other kind of speed-ups known for Bender's decomposition. We really wanted to see what happens if we apply bare-bone methods. Is there any advantage of using adaptive Bender's cuts? And what you can see is that so the red line is are the results for the adaptive. And here we see the cumulative performance profiles, which means that on the y-axis, you see the percentage of instances solved, and on the x-axis, you see the time in hours, okay? And as the number of scenarios increases from 100 to 5,000, we slowly start to see the advantage of applying adaptive Bender's cuts over the other two methods. And that, of course, this becomes really prominent by 50,000 of scenarios. So you may say 50,000 is huge. Are we really solving 50,000 of scenarios in the real world? Probably not always, but what we have seen is by comparing the in-sample and out-of-sample results is that indeed, even for 50,000 of scenarios, we were still getting different solutions, which means we were still not converging to the true optimum. Okay? Okay, and then when you look at the gap over time, here again you see that the adaptive approach, here on the y-axis you see the value of the gap that goes down to 0 much, and then again here in hours, much faster than for the other two approaches. Okay, when we compare the deterministic equivalent with the classical generalized adaptive partitioning, which, remember, solves MILP in each iteration, and our Bender's cut. Here you can see, let's just focus on the number of instances solved to optimality. Here you see that adaptive, again, outperforms the standard approach, especially for the cases with the large number of scenarios. Now let's move to the conditional value at risk problem, facility location. Again, I would say it's a really, really simple problem, but great to illustrate the power of Bender's decomposition, and in particular of adaptive Bender's cuts in such situations. So we will assume now that to here and now, we have to install some facilities. So we are given a set of potential facility locations I and clients J. We have fixed installation costs, and each facility has a capacity. And now there are transportation costs for each unit of the demand. And again, demand is not going to be certain. So we have somehow to install facilities today, then their demand is revealed, and then we will have to assign this demand to the closest open facility while respecting the capacity of that facility. And in the standard expected value optimization, you would say, I'm going to assign to the closest open, and we will minimize the expected costs of allocation. But in the conditional value at risk, we will assume that we are dealing with a risk-averse decision maker who is focusing on the worst case realizations. So not necessarily on the worst case scenario realization, but let's say what happens, let's say in the 10% of the worst case scenarios. And now I want to minimize the expected allocation costs for the worst case 10% realizations. Okay? So the value, so our decision is which facilities to open. This is here and now. In the second stage, upon the realization of this uncertain demand, let's call it D tilde, each client is allocated to the closest open facility while respecting the capacities. The goal is to minimize facility installation costs from today, plus the expected value of the worst alpha quantile of this random distribution, over the random distribution of the transportation cost. So let's look at this visualization to understand a little bit better what is going on. So if these are my facilities that I want to open, and these are the clients that have to be served. So if we open facilities 1, 2, and 3, we will do some kind of allocation, okay, while respecting the capacities. So for each possible realization of these uncertain demands, we will have different allocations and we will have the allocation costs. So these allocation costs will be a random variable on its own. And now if we try to represent using a histogram the costs of this allocation for different scenarios while keeping my decision of open facilities like this, then we will get this histogram here, which means the cost can be 20, 19, and so on. And now I want to focus on let's say alpha is 90%, and then I say, okay, if at alpha is 90%, this is my conditional value at risk. And from there on, now I focus on these worst case 10% realizations. And now what is the average cost for these 10% of worst case scenarios? This is what is conditional value at risk, and this is what I want to minimize now. So if this value of alpha, if we move it between 0 and 1, then we will end up, if alpha goes to 100%, then we are actually optimizing expected value. If alpha goes close to 0, then we are optimizing the worst case scenario. So that's why CVaR measure is very powerful and it contains as a special case what we have seen as the expected value. Okay, so can we actually, how do we model this? And then there is also another seminal result from Rockefeller and Uriassev from 2000, in which they have shown that this CVaR value can be actually represented as a linear program as well. And for that, we need an auxiliary variable. So this is the problem that we are solving. So we decide which facilities to open. These are our X variables. We want to make sure these facilities have sufficient capacity no matter what happens with uncertainty. And then we want to minimize conditional value at risk for the given value alpha. Okay? So this conditional value at risk is actually so the value q, the function q, is just our allocation function. This is what I said, our random variable that we look at. And this is just the minimum allocation. So by the result of Rockefeller and Uriassev, we introduce an auxiliary value theta, which is going to be the value at risk for the given alpha. And these are going to be the excess values. So the so ZS will be actually for the scenario S, the difference from VAR to the real measure value of, let's say, if that was 13, I don't know, and this is 16, then for this scenario here, the Z is 3, the difference between them. And so we end up with a huge deterministic equivalent again, which is MILP, that we can solve using the solver as if we want. But what we want to do is, again, apply Bender's decomposition to this model. And as you can see, again, this is going to decompose by scenarios because we have one constraint for each scenario. So we will have a nice block angular structure. Once we fix the variables X, we have linear programs. We do the same LP duality reformulation, and the Bender's cuts, they just look like this. So we are going to, if you use multicut approach, you would replace each of these terms here with the variable theta s, and you will get a cut like that. And again, now we can exploit the idea of adaptive Bender's cuts. And the conditions that apply in this particular case, again, it's very technical. When you look into these formulas, they end up in our case to the situation that we are going to do the refinement based either on the equal demand or on the equal value of particular dual solutions. So if they are the same, the scenarios stay the same, otherwise we have to separate them. And so let's move now to the computational results. So we call it branch and Bender's cut. And I guess from what John was saying, branch and check and branch and Bender's cut, the major difference is that these Bender's cuts are globally valid. So we don't add them only for the subtrees, for the subproblems, but they are globally valid in the whole branch and bound tree. And partitions that we find on the way, they are also applied globally, everywhere in the tree. And as I was mentioning, there is no sophisticated implementation. It's really bare-bone Benders, just to see the effects of adaptive Bender's cuts. And again, we have similar kind of performance cumulative charts. And here red again stands for the adaptive. And you can see that now already for more than 1,000 scenarios, we have a clear advantage of using adaptive versus both single or multicut, or of course versus deterministic equivalent. And the deterministic equivalent, unfortunately, already for 2,000 scenarios, cannot actually solve all of these instances from our benchmark to optimality. And then one more table in which we also wanted to have a closer look into the times of the deterministic equivalent, the number of optimality cuts that we are adding in each of these implementations, and for the adaptive also the number of refinement steps. So how often, how many iterations of the refinement do we need? And as you can see here, actually this number of refinements stays below 25, and the size of these partitions stays pretty small, which was really nice for this particular case. Of course, as I was saying, here you can see the number of separated cuts is 500,000 for the multi-cut implementation, is very small for the single cut implementation, and for our adaptive, we are somewhere in between. Okay, so to conclude, we see that these adaptive cuts, they combine the strength of both in terms of computational efficiency, that you should not bother implementing them if the number of scenarios is rather small. It doesn't pay off, okay? However, you might consider them not only, as I said, not only for the stochastic problems, but also for the deterministic one. Think of scheduling problems, think of facility location. Whenever we have this separable substructure, where we have many subproblems to solve, maybe we don't have to solve it for every single subproblem. Maybe we can aggregate them and look at the representatives and then only do this disaggregation on the fly. That's the major message. And I have to say that there are still a lot of open problems. For example, if you implement it in a branch and cut fashion, whether you want to keep partitioning within the subtree being the same and different in the other subtrees. We didn't do that. So what the partitioning that we apply is, if I am in a certain node of the branching tree, I find the partitioning there, I will apply it globally. So it's a heuristic, but certainly we can do much better than that. Okay, so thank you very much for your attention, and hope there will be some questions.